Hi guys, I want to talk today a little bit about formal charges. Formal charges are really useful for when we're putting together Lewis dot structures because they give us a way to predict how valid the structure is, how stable the structure is going to be. And it really gives us a way to formalize kind of the basic way that we teach you guys to put together Lewis dot structures. So we give you kind of the tools to do so, but the reason for those tools are these formal charges. So you can always check a Lewis structure by calculating the formal charges to kind of predict and be able to get some information about how stable it is in that particular form. This helps with things like isomers, it helps with things with like resonance structures, and it helps you to be able to figure out, if you aren't certain, how to connect elements together to make these molecular compounds. So let's get right into it. A formal charge is a comparison of the number of electrons that are in the valence of that particular element. So based on their location on the periodic table, based on their electron configurations, those highest energy electrons, how many are there? And that's of course based on their column, based on the group. And we subtract from that the number of electrons that are actually in the structure in the way that I've drawn it. And the difference between those, if there is one, right, if they aren't the same number, is the formal charge. So let's consider this carbon-oxygen dichloride molecule. Let's see how many valence electrons we're working with here. So carbon has 4, oxygen has 6, and then chlorine has 7. So we have 2 times our 7 is 14, 24 electrons total to work with. Now, when you are learning Lewis dot structures from a basic kind of standpoint or an introductory standpoint, then we usually tell you that the element that either comes first in the compound or wants to make the most bonds is going to be at the center. And that's true, but the reason for that is because it'll usually follow the formal charge pattern that way. So let's put our carbon at the center here, and let's put a couple chlorines on there, and an oxygen. So I've used up then 2, 4, 6 in just the bonds here. So I've used up 6 of those electrons. I have 18 electrons to play around with. So I'm going to put them as pairs on my outermost atoms. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, and I've run out of electrons to use. So that's all 24. But this isn't a great Lewis structure. It's problematic because my carbon doesn't have a full valence, right? It has only 6 electrons there, and we want to have a full. So we could do something like share a pair here maybe, and that would give me a structure that looks like this with a double bonded oxygen attached to a chlorine on each side. But why can't I just say, well, I could have done this one, right? Why not have, here's my chlorine attached to the carbon and double bond this guy. In terms of the number of electrons, and in terms of my overall structure, there's no reason that I couldn't do that. But let's evaluate these two structures using formal charges, and then we'll talk about what those formal charges tell us, what they mean in terms of chemistry and the validity of these structures. So if we go back to our equation, if you want to think about it that way, this isn't super high level math or anything. If we look at the number of valence electrons that chlorine has, that's 7 from the periodic table. And we know that because it's a halogen. So it's in column 17 or 7A. So it has those 7 valence electrons. Carbon here has 4. Oxygen has 6. So we know that that's what I'm starting with for each of these guys. And same with these while I'm on a roll. Okay, so that's the number of valence electrons. Now I need to count out the number of electrons that are within this molecule. So how do I do that? Well, in a bond, we would say that anything that has a bond between them, this is equivalent to 1 electron each for the atoms that are sharing it. So for this bond, one of the electrons is associated with this atom, one of the electrons is associated with this atom. So we count each bond as 1 electron for the atom that it's connecting to. If we have a lone pair of electrons. That's a non-bonding pair. Both of those electrons are associated with the atom that they're on. Okay? And then if we have, double bonds or triple bonds, then the number of electrons is the number equivalent to the number of bonds, the number of shared pairs there. So one each for however many pairs there are. So let's use this accounting then to figure out what we have going on for this chlorine. So it wants 7, that's how many it should have on the periodic table. In this structure, I have 2, 4, 6, and then 1 from the bond is 7. So if I take the difference between these two, I get nothing. Okay? My carbon here wants 4. It has 4 valence electrons. I have 1, 2, 3, 4 from my bonds here. So it has 4. It has 4 in this structure. That gives me 0. For this chlorine, it's the same as this guy. It looks the same, right? 3 lone pairs and the 1 from the bond. So that's 7 as well, which gives me 0. And for my oxygen here, it has 2, 4 in the pair, 5, 6 from the 2 bonds. So 6 from the periodic table, 6 on this structure, gives me a net formal charge of 0. Now all zeros is a good thing. We don't like formal charges. If I have little pockets of weirdness or pockets of charge, that usually means that there's kind of some instability there in that structure. So this is a nice structure. It's got good symmetry, doesn't have any formal charges on it, so we like that one. It looks like a lot of work to just get a lot of zeros, but there you go. Let's compare it to this one and see what we think of this guy. So if we start with our oxygen up here, oxygen has 6 valence electrons, but in this structure it has 2, 4, 6, 7 from the bond. So it has 1 more electron than I normally would have, which gives it a net -1 charge. And again, it's not a charge like we think about it with ionic compounds, but this is a formal charge, meaning that there's kind of a pocket of weirdness because of the way these electrons are distributed and the way that I'm understanding them and writing them in this model. Now this chlorine has 2, 4, 6, 7 from the bond, so it wants 7, it has 7, so that gives me a net charge of 0, so that's good. Carbon here has 4, wants 4, net charge of 0, so that's good. This chlorine, it wants 7, right? It has 7 valence electrons, and I have 2, 4, 5, 6 from the bonds. So it has 1 fewer than it normally would like, which gives it a net positive charge. So there'd be a positive formal charge on this chlorine, a negative formal charge on this oxygen. And anything that has formal charges on it is going to be unlikely or less likely to occur. It's not never, it's just highly improbable. And now this structure then would be the one that I would predict would be the one that forms from a stability standpoint for this particular compound. So let's talk about these rules then, because I keep referring to them without really explicitly stating what they are. So let's talk about these formal charge rules. Now, the most zeros win. The structure with the fewest formal charges is going to be the most likely. If there are formal charges, if they're close to each other and we have like charges that are near, so like on adjacent atoms, for example, if I have a positive formal charge near another positive formal charge or a negative near another negative, then that structure is highly improbable. That's closest to never and closest to impossible as I ever like to be. I'm always a little bit cagey about my always never language, but in this case it's very close to never that this is going to occur because it's very uncomfortable that way. And again, I'm kind of anthropomorphizing there because it's not like a molecule can be comfortable or uncomfortable, but we're talking about energetically favorable or unfavorable. Now the last rule is if we have two structures that have the same formal charges, if the negative formal charge is on the more electronegative element, then that's more likely. So if the negative charge is on an oxygen, for example, or a fluorine, then that's going to be more likely. Even though it has formal charges, it can still exist that way. And the way that it will most likely exist will be with that negative in the more electronegative kind of spot. So let's look at another example. Let's look at SO2. Sulfur dioxide, I have 6 from my sulfur and 6 from my oxygen, so that gives me 8 electrons total to work with on this structure. When you put them together, there's kind of a couple ways that we can do this. We can end up with sulfur at the center, and we have something that looks like this. And if you have questions on how I get to these, then feel free to reach out. I'm happy to help. So this is one option. It's also just as likely that I have a double bond on each side. As long as I still have the right number of electrons on the whole thing, then that should be fine. All I did is I zipped those up there. And now, why is sulfur at the center? Well, in general, chemical compounds and nature, I would say, like symmetry. So we like to have kind of the weird one at the center and then the other things on the outside, but there's no reason that there couldn't be an oxygen at the center. So why don't we draw that one too? And we'll evaluate it as well. And then we can do the same sort of operation. It could be double bonded either way. Okay. All right. So this is weird. These guys look really weird. If you have any sort of chemical intuition, you look at those and you just go, ugh, this feels awkward. But let's look at formal charges because that's what we're practicing here. So all of these guys have 6, right? All of them have 6 valence electrons. So that's always what we're going to be comparing it to. This oxygen in this structure has 7 though, right? So it 6 valence electrons minus the 7 that are there, it has 1 fewer electron, or 1 more electron, which gives it a negative charge. My sulfur here has 1 pair, and then 1, 2, 3 from the bonds. So valence electron 6 only has 5, gives a net +1 charge. And then my oxygen here has 6, wants 6, so it has a net 0. So we have a formal charge of a +1 on the sulfur, -1 on the oxygen. Now if we do this guy, has 6, wants 6, 0 on this guy. 1, 2, 3, 4 from the bond, 5, 6 from the lone pair, has 6, wants 6, so that's good. Has 6, wants 6. So this one looks like a nice structure, right? No formal charges. That looks pretty comfortable. So even though sulfur here has 2, 4, 6, 8, 10 electrons in its valence, it's still happy in terms of formal charges. So it's breaking the octet rule, but by the formal charges, it's telling me that this structure is valid and that there's a way to kind of evaluate that, even though it goes against our beloved octet rule. Okay, let's do the same thing here. So has 6, wants 6, 2, 4, 5, 6. This one has 5, 1, 2, 3 from the bonds, but wants 6, so this guy has a +1. This one has 7, but wants 6, so that gives you a negative. And then this one has 6, wants 6, so we're good there. This one's 6, and then 1, 2, 3, 4, 5, 6. And this one, 6 and 6. Okay, so if I was looking at these, I would say that these are the most likely, right? Because they have 0 formal charges. So based on our rules, then I would say if I was going to evaluate between these two, the symmetry part of this is going to lead me to this one. This is just an awkward looking thing. And this has to do with things like atomic radius and the differences in electronegativities and all the other kind of things. But based on just the formal charges alone, this is a valid Lewis structure, right? There's more that goes into this. It's more complicated, but this just gives you a way to check it out. Now, if we look at these other 2 options as kind of the which is the next one, well, this has a negative on my oxygen. This one has a positive on my oxygen. So I would say that this one is going to be the next most likely, as opposed to this guy, because the negative charge is on the more electronegative element. Oxygen is more electronegative than sulfur. So again, this gives me a way to kind of evaluate and validate the different structures that I have, and it's based on these rules of formal charges and this quick kind of back of the envelope calculation we can do based on the valence electrons and how many they have in these structures. As always, if you have any questions, don't hesitate to reach out. Otherwise, I will talk to you again soon.